Hi everyone, we are going to continue doing some examples from chapter 8, and those examples are just going to still go through isolated systems and non-isolated systems, and then also thinking about conservative and non-conservative forces, and how do we calculate work, or how do we calculate speed, or how do we calculate the force of friction that's acting either in an isolated or non-isolated system. Okay, so this is a slide that we want to start off on today. So this says that we have a block of mass 1.6 kilograms is attached to this horizontal spring here, and it has a force constant, so that's our K, of 1,000 Newton per meter. It says that the spring will be compressed. So remember, it's starting here at its equilibrium position, and now we're going to compress that spring. We're going to compress it 2 centimeters, and then we're going to say after we've compressed it, we're going to release that block. So the first part of this question says to calculate the speed of the block as it passes through the equilibrium position, x equals 0, and let's assume that the surface is frictionless. So let's calculate speed, and we have to assume that the surface is frictionless. Okay. Okay, so in this problem, first thing is I want to think about this as I have the system is the block, and I know that that block is being acted on by the spring. It is frictionless, but they are telling me ultimately that my block is passing, my block after I've compressed it based on this, I've compressed the spring, I have my block, then we'll release it, and that spring is going to act on the block to move it so it'll have some type of change in velocity or change in speed. So I would think about this system for the block as a non-isolated system. So in this situation, let's think about things that we know. We know that the block is first going to have an initial velocity of just 0 because it's at rest when it's close by this spring. And then I know that I'm going to compress the spring, so we'll call this x based on spring compression, so for the spring. We're compressing that spring, and it was 2 centimeters, but actually we know that that's 0.02 meters, and since the equilibrium position, because here's my spring, here's my block, if this is at x equals 0 and we're compressing the spring, then technically this should be a negative 0.02 meters. Couple other things that I know are that the spring is going to do some type of work on the block. So the spring is going to do some type of work on the block, so I can say that the work done by the spring, we can find that, is just equal to 1/2 kx squared. So we can actually calculate the work done here by the spring on the block. So we know K, they gave us K, that was 1,000 Newton per meter. And we know X, it was compressed a negative 0.02 meters. So if we plug that in, 1/2 times 1,000 Newton per meter times my compression, negative 0.02 meters, but we're squaring that, we should get the work done by the spring on the system, we should get that to equal 0.2 joules. Okay, now they asked us in the problem to calculate speed of the block. Well, I know that my work kinetic energy theorem can come into play because the work that's being done by the spring on this object should be equivalent to the change in kinetic energy of that block or of that mass. And we already know this because we calculated it right here. So I know that this is 0.2 joules. We know delta K is just equal to 1/2 mv final squared minus 1/2 mv initial squared. Well, we just said that since our block started off at rest This initial should just give us 0, because if the initial velocity, if my initial velocity is 0, that whole thing just becomes 0. So then we can find our final speed by just plugging in our values that we have. So again, we knew the work done by the spring on the block was 0.2 joules. We found that up here. That equals 1/2. The mass of the block was 1.6. Yeah, 1.6 kilograms. And we're trying to find that final speed. So then if I multiply these, divide, and then square root, we should get our final speed to be 0.5 meters per second. So this problem we can just think about using our work kinetic energy theorem. Now, because we didn't have to think about gravitational potential energy here, solely because I'm not changing in height, I'm not changing in that y direction, so that delta UG is out here. Okay, let's look at the second one. The second part of this question says, calculate the speed of the block as it passes through the equilibrium position if we have a constant friction force of 4 newtons that's going to start to slow that motion from the moment that it is released. So I want to know what would the speed of the block be as it passes through that equilibrium position if we have our frictional force that's acting on it to slow it down from the moment that this block is released here from that spring compression. Okay. So now on this one, here's my spring that's really compressed, here's my block, and we're going to release it and it's going to be moving that way. Okay, so in this case, this one's different in that now we have a non-conservative force that's also acting. So I am going to have my work done by the spring on the block, and that work done by the spring on the block should be equal to that kinetic energy, my change in kinetic energy. That's based on the work kinetic energy theorem. But I also have to include now friction. So I'm going to add here my change in delta E INT, remember, which is that change in internal energy, aka friction. So my work done here by the spring on the block, we actually already found that in A. We found that to be that 0.2 joules, because remember we just compressed the spring with this block and it didn't change from problem A to this problem. So remember we got the 0.2 joules just from the problem beforehand. So we can just go ahead and write that one here. Our delta K, our change in kinetic energy, we know that that's our 1/2 mv final minus our 1/2 mv initial squared. Okay, well at first, after we've compressed the spring, that means that before I let this go, the block is then at rest. So its initial velocity then must be 0. So now this must be 0, so it's out. So I'm trying to find, again, that speed here after we've released that block and it's moving back past that equilibrium position. Okay, so I have 0.02 joules equals my 1/2, here's my K, 1.6, yeah, that was the mass, 1.6 kilograms. I'm trying to find that final velocity squared. The only difference between this and the last one was that now we have friction in play. And delta E, I'll put those in brackets to represent that this is my delta K. Delta E, my internal energy, my change in internal energy, is just that frictional force times the displacement. So I know that it's moving from where it was compressed to the equilibrium position. And they told us that the frictional force here is simply 4 newtons. They gave us that in the problem. So they told us in the problem we had frictional force was 4 newtons. And then we know that the displacement was the negative 0.02 meters. Okay, so then if I do my math here, we should get 0.12 joules and that's going to equal my 1/2 times 1.6 kilograms times VF squared. So I just multiplied those, and then I added it over here, or yeah, I have it over here now on this side. So now if I simplify this, we should get VF to equal 0.39 meters per second. Okay, in the first problem, we got our speed of that block to be 0.5 meters per second. When we have friction now, we get our speed of the block to be 0.39 meters per second as a final velocity, or as a final speed. So this should make sense that friction should slow that final speed down. So we should logically get a smaller number when friction is in play versus when friction isn't in play, and we do. We see that this one was 0.5, we see that one was 0.39. Okay, so just like we can think about our work kinetic energy theorem, we can also, and we can also think about how friction comes in with that. We also may have some changes that happen with potential energy, also with kinetic energy, and if we have friction present, now it's getting really complicated. So let's look here. If a friction acts within an isolated system, then we know that our change in mechanical energy is just equal to the sum of all of the kinetic energies plus the sum of all of the potential energy. So we knew that from before. But we can also say that if that's for an isolated system, it can also equal a negative my work done here by friction. So what happens though if we have non-conservative forces like friction that's acting in a non-isolated system? If we have friction acting in a non-isolated system, then we're going to say that the change in mechanical energy is going to be equal to the negative work done here by friction plus the sum of the work done by all of the other forces. So we can kind of rewrite this equation down here. So I can also say that the sum of the work done by all of the other forces is simply equal to, if I'm thinking about my mechanical energy, the change in kinetic energy plus the change in all of the potential energy, and then plus my change in internal energy, which is just friction. So writing this is just another way to get this. This is probably just more elaborate, knowing that our mechanical energy is equal to delta K plus delta U. And then I know that this work done by friction is also equivalent to my change in internal energy. All of these added up should equal the sum of the work done by all of the other forces. So let's actually do some examples where we're utilizing this, because we may see that we don't need all of these, and all of these may not be in play every single time. Okay, so in this problem we have a 3-kilogram crate slides down a ramp. This ramp is 1 meter in length, and it's inclined at an angle of 30 degrees. The crate starts from rest, so it's right here at the top of the truck, or the top of that ramp, starts at rest, so its initial speed is 0. And it's going to experience a constant frictional force of 5 newtons. It's going to continue to move a short distance until it gets onto this horizontal floor, and then that will happen after it leaves the ramp. So we have the first question says use energy methods to determine the speed of the crate at the bottom of the ramp. So initially it was at 0. It's going to move down this ramp. Friction is in play here. I want to know the speed of that crate at the bottom of that ramp. So I've asked you to use energy methods because of course you can do kinematics with this. But it's important that we know not only how to do this with kinematics, but also how to do this with energy methods. So let's do this first problem. Okay, on the first part, we want to think about, is this an isolated system, or would we think about this as more of a non-isolated system? So we know that friction is acting. Will you close that door, sweetheart, for me? We know that friction is acting on it. So we can think about the system as being the crate and the ramp and the earth. So maybe I can think about all of those things acting as a system. And if I model those three things as a system, I have the crate, I have the ramp, so I'm going to have friction within my system. And then I also think about the earth, so I know that I have some type of gravitational potential energy. If I think about all of those as a system, then it can be an isolated system, or just have a non-conservative force acting on it, which is friction. Okay, so if we want to find in the problem the speed of the crate, we want to find VF. That's our goal. What is a VF? We know that for an isolated system, that mechanical energy is equal to 0, right? That's just what's known for an isolated system. Now, we also know that that is equal to the sum of all the kinetic energies plus the sum of all of the potential energies, so that's equal to 0. But now we have a non-conservative force that's also in consideration. Remember, we have friction. So I not only have to have this, but I have to show delta K plus all of my changes in potential energy plus my change in internal energy, which is friction. All of that is equal to 0. So I have some kinetic energy, I may have some change in gravitational potential energy, and I'm going to see some change in internal energy based on friction. All of that should equal 0. Okay, so what we know is we know that delta K is just 1/2 mv final squared minus 1/2 mv initial squared. Well, we also know that the box is starting at rest, so that initial must be 0. And then if I'm thinking about my potential energy change, we don't have a spring here, so then that means the elastic potential energy is out. We do, though, have a movement in the y direction, so we'll call that my change in gravitational potential energy. So we'll call that delta U sub g. We know that would be equal to mg y final, so that final y position, minus mg y, that initial y position. And then my change in internal energy is simply just my force of friction times that displacement. Okay, what else do we know? So we knew that this one was 0. Another thing that we knew let's go back to that picture, guys. Our final y position, so our initial y position was at this 0.5 meters, but our final y position is going to be at 0. So I know, too, that this mgyf, if this final position is at 0, that whole thing is at 0. So now that's gone. So let's rewrite this. We have 1/2, and let's also plug in numbers, because we know the mass of this was 3. So 1/2 times 3 kilograms times the VF squared. That's my goal. That's what I want to find. Plus, minus, because this is plus a minus, minus the mass, 3, times acceleration due to gravity. And then that initial y position was 0.5 meters. They told us that the force of friction in the problem was 5 newtons, so I know that this value is just 5. So we'll say that's 5 newtons. And then the displacement is just going to be the length of the ramp, which was 1 meter. All of that should equal 0. So ultimately, if we just do some rearranging here, I'll find my number for this, my number for this. I'll add this over to this side, subtract this over here, and then if I divide by this, our final speed after we square root should be 2.54 meters per second. Okay guys, so I'm going to stop the video here. I'm going to have another video finishing up the chapter, and yeah, I will continue this later. Bye!